and welcome back. Today we're talking all about waves.
By the end of this episode, you'll know what a wave is, what the different parts of a wave are, and you'll have fun demos to share with your friends.
So what exactly is a wave? Well, simply stated, a wave is a disturbance that travels through a medium with no actual transport of matter. The source of any wave is a vibration, or repeated back and forth motion amongst an equilibrium position. This vibration then causes a wave to form, which travels through a medium.
The time of one back and forth motion of a vibrating object is a period. For example, a pendulum. The period of a pendulum is the time for it to swing forwards and backwards one time. Just like that. The length of the period depends only on the length of the string and the acceleration due to gravity. Does not depend on the mass at the end of the string. Don't believe me, kids? Let's do an experiment. Pendulum with a long string. Let's time its period using a stopwatch.
Its time was 1.19 seconds.
Now let's measure the time of the period for a pendulum with a shorter string but the same mass at the end of the string.
Its period was 0.69 seconds.
As you can see, as the length of the pendulum decreases, so does the length of the period. But as the pendulum length becomes longer, so too does the period. This relationship between the pendulum string length and the period is direct. Fascinating.
Wow! Now let's talk about the different parts of a wave. Many different parts. The high points on a wave are known as the crests. The low points on a wave are known as the troughs. This dashed line here, this yellow line, represents the midpoint of the vibration. An amplitude is the distance from a crest to the midpoint, or a trough to the midpoint. The pink line here represents the wavelength of a wave, which is the distance from a crest, or a trough to a trough.
Frequency is the number of vibrations per unit of time. In the pendulum example, it is the number of back and forth swings per second. In the example of a wave, the frequency is the number of wavelengths per time. Frequency is measured in per seconds, or commonly referred to as hertz. Frequency and period are inversely proportional, meaning frequency is equal to 1 over the period, and period is equal to 1 over the frequency. Let's take a few seconds to do a problem. Sam the fly flaps its wings back and forth 121 times each second. The period of the wing flapping is what?
Take 10 seconds to solve the problem. Pause the video if you need more time.
Since the period is equal to 1 over the frequency, to find the period of the flapping of Sam's wing, you divide 1 by 121 hertz to get 0.008 seconds. As we discussed earlier, a wave is a disturbance that's transmitted from one place to another. This means that energy is being moved from one place to another by passing through something else, like water or air. The water itself is not being moved, only the energy is. Let's take a look at a jump rope for an example. As the energy moves horizontally through the jump rope, the matter that makes up the jump rope doesn't actually move. It merely provides a medium through which the energy can travel. A similar example involving water demonstrates this idea as well. Drop this stone in the water. Watch as waves ripple out from the center. Ready, kids? As the stone is dropped in the water, a circular wave moves out from the source. However, only the energy is moved. The water molecules themselves remain in their original locations.
One of the interesting properties of a wave is its speed. Its speed can be calculated by multiplying its wavelength, which is represented by this Greek symbol lambda, and its frequency together. Now let's calculate the speed of a wave. Here we have a wave with a frequency of 10 hertz and a wavelength of 30 meters. What is its speed? Take 10 seconds to solve the problem. Pause the video if you need more time. If you got 300 meters per second, you've got the correct answer. Let's see how we got it. So first, you plug in your variables. 30 meters for a wavelength, 10 hertz for a frequency. And when you multiply those two together, you get a wave speed of 300 meters per second. Great job! There will be two types of waves that we'll be learning about today. Transverse and longitudinal waves. Let's take a look. A transverse wave occurs when the motion of the medium is at a right angle to the direction that the wave travels in. Examples include those of musical instruments and any wave in the electromagnetic spectrum. Longitudinal waves occur when the direction of the medium is parallel to the wave. The wave in the medium would be traveling in the same direction, as shown here in this video. An example is a sound wave. When two waves meet at the same place at the same time, a phenomenon known as interference occurs. At these points, called interference patterns, the wave's effects could either be increased, decreased, or neutralized. Let's take a look at two main types of interference, constructive and destructive. Constructive interference occurs when the crest of one wave meets the crest of another. They overlap, and then their individual effects add together. This is termed reinforcement. The resulting amplitude of the new wave, therefore, is larger than the two original waves. Destructive interference occurs when the crest of one wave overlaps the trough of another wave, and the individual effects of the wave are reduced or completely neutralized. This is termed cancellation. There are two possible outcomes of deconstructive interference. As the first image shows, it could result in a wave with a smaller amplitude, or a lower crest than the original wave. This is when the two waves have different amplitudes when they cross paths. It could also result in the wave being neutralized, as shown in this image. This results in no wave. This occurs when the crest and the trough of each wave have an equal amplitude, and when they overlap, there is no wave. Now, let's look at standing waves. In this video, Sarah is shaking a rope which produces a type of wave called a standing wave. A standing wave does not seem to move and instead appears to stay in one place. The parts of the standing wave that remain stationary are known as nodes. The parts of the waves with the highest amplitudes are called antinodes. They occur halfway between each node. Standing waves occur because of interference between the wave and its reflection off the tree or the wall, depending what you're using. If Sarah were to shake the rope at a different frequency, she would be able to create different standing waves. The higher the frequency, the more interesting the wave. The frequency, though, would have to be a multiple of a half of a wavelength of the original standing wave that she created.
Next, let's look at a phenomenon known as a Doppler effect and how it pertains to moving sources of sound.
Do you hear that, kids? The cops! They're coming for me! Let's see how the Doppler effect changes the pitch of the siren.
As the wave source, or the siren, approaches Sam, she encounters the waves at a higher frequency. The reverse is true as the siren moves away from her. She begins to encounter the siren with a lower frequency. As the frequency increases, so does the pitch. This relationship between the frequency and the pitch is said to be direct. This phenomenon is called the Doppler effect. The greater the speed of the source, the greater the Doppler effect. Now let's look at two specific types of waves, bow waves and shock waves. The first type of wave, a bow wave, occurs when an object's speed is faster than that of the waves produced. This is demonstrated in the figures on the right. The bug's speed is greater than that of all the waves. In the image on the left, the first image, the speed of the bug is less than the speed of the wave, and a bow wave is not produced. In the second image, the speed of the bug equals the speed of the wave, and again, a bow wave is not produced. For the images on the right, the faster the speed of the bug, the more narrow the angle for the bow wave. Now let's look at an example of a bow wave in nature. Watch as the bug swims through the water and creates a bow wave. But look closely, kids, it only happens for a fraction of a second. Did you catch it? Let's watch it again. That's cool, right? Next time you're at a pond, keep an eye out for the bugs and the bow waves they produce. They're all around you.
Now let's talk about shock waves. Boom! A shock wave is a three-dimensional wave that happens when an object, like a plane, travels faster than the speed of sound. The wave that is created has a conical shape behind the moving object. When the wave reaches a listener, a loud sound is heard. This sound is known as a sonic boom!
A common misconception regarding sonic booms is that a sonic boom occurs at the moment an object surpasses the speed of sound. In reality, the boom occurs when the wave reaches the listener.
Now let's look at the conical sound waves that are produced by a plane moving faster than the speed of sound.
This eraser represents a plane, and this folded piece of paper represents the conical sound waves produced by a plane. Notice how its shape is 3D, like an ice cream cone, and how the waves follow behind the plane as it travels through the sky.
Wow, we've learned a lot today. We now know that a wave is a disturbance and is caused by a vibration.
We know how to calculate the period for a given frequency, and the speed of a wave can be found by multiplying the wavelength by the frequency.
We've also learned the difference between transverse and longitudinal waves,
and have looked in depth at many different types of interferences and waves.
Thanks for watching, kids!